Thanks, Fraser. So indeed, I promised by the end of this talk, we're going to come back to SERSI. Specifically, we're going to talk about one situation in which we were able to partially verify a key component of SERSI. But first, we're going to talk about what might seem like something else entirely, a new development in SMT solving, the ability for SMT solvers to reason about equations over a finite field. The motivation for this is very much zero-knowledge proofs. And so I'm going to put a pipeline up that I guess you basically saw in the last talk, the way that zero-knowledge proofs are dominantly used. Someone starts with a high-level idea. They take that idea and through programming and compilation, turn it into equations over a finite field. This is the circuit that you saw in the last talk. And then they feed those equations into a zero-knowledge proof system, which basically just gives them their private application. Of course, this is a simplification, but this is more or less how the pipeline works. And this pipeline already as drawn is somewhat concerning because we know that any time that people program, they make mistakes. And bugs in the system of field equations can have very bad consequences for the downstream application. Let me give you an example. It's totally possible that there's some bug in a set of field equations that define a private cryptocurrency, which would render the cryptocurrency insolvent. The bug would allow someone to spend money they don't own or print money out of thin air, but would not compromise the privacy of the cryptocurrency. And so it would be very difficult to discover whether anybody was actually exploiting such a bug. Given that there's the potential for very serious bugs, and moreover, we have reason to believe it would be hard to detect that they are being exploited, we're very interested in trying to get rid of bugs. And so the natural question is whether or not we can verify that some system of field equations is a correct representation of some high-level idea. This is, of course, the classic verification problem, but it's extra difficult in this setting because of a domain separation. You see the specification here is probably written over high-level spaces. Boolean reasoning expressing who can spend money and when. Bit vectors fixed with integers expressing how much money somebody has. Arrays representing the global state of the system. But the implementation is just field equations. And the stuff on the left, that's stuff that our existing automatic reasoning tools like SMT solvers can understand reasonably well. But equations in a finite field, prior to our work, were not something that an SMT solver could understand. And so what would you have to do if you wanted to solve a verification problem of this kind? You'd have to map those field equations into integer equations evaluated modulo a prime p, or perhaps fixed width integer equations evaluated once again modulo a prime p. The common thread here is reasoning about the modulus operation directly, which is very challenging in the general case. And that means that these kinds of approaches are more or less dead in the water. So what we do in this work is we do the direct thing. We add finite field reasoning to an SMT solver. How do we do that? Well, we start by specifying a theory of finite fields, a language for talking about field constraints. Then we give a set of verification problems that are written in reference to this language. These verification problems encode whether or not particular outputs from a ZKP compiler are correct representations of a particular input. We then give a decision procedure, a theory solver in the context of SMT that's capable of solving field equations using a lot of classic ideas from computer algebra, but also avoiding one classic idea called a field polynomial that, as you will learn in this talk, is totally unsuitable for this use case. And then finally, we code all this up inside CVC5, an SMT solver that we built at Stanford, and see that it works dramatically better than the previous approaches in practice. So taking a step back, if you imagine automated verification as being some kind of dream house that we would like to construct, here really we're focusing on the foundation, the solver technology that you can build automated tools on top of. We hope that by adding field reasoning to this foundation, we make it possible to do automated verification in the presence of finite fields. And at the end of this talk, I'll come back to how we were able to do that in one instance inside of SERSI, looking at what we call its field blaster, its finite field blaster pass, which is the final pass or one of the final passes when you're lowering to zero-knowledge proofs. So this is the order of events. First up, finite fields. I should probably remind us what finite fields are. For the purposes of this talk, we're going to be talking just about prime order finite fields, which are always isomorphic to the integers mod p. We write them z sub p, and the set of values that you can have is 0 through p minus 1. The operations that you can do, addition, multiplication, and equality. And just a clarifying note, we're assuming here that p is fixed and the solver knows it up front. So p is not some variable that can be determined by another part of the logical formula that you're trying to solve. Just a few examples. First, x equals x plus 1 or y squared equals y. This is an example of a formula that we would like to determine whether or not it's satisfiable in some field. Let's say the integer is mod 5. Here, the formula is satisfiable because if we set y equal to 0, the second constraint is satisfied, and so the first constraint doesn't matter. On the other hand, if we had just the first constraint, x equals x plus 1, this is unsatisfiable, and the integer is mod 5 because nothing is equal to itself plus 1. In fact, this would be unsatisfiable in any finite field. So these are simple formulas, but what are the formulas that we actually want to check? Well, they correspond to verification problems, so let me give you those. We're going to be checking whether or not some Boolean function, a Boolean formula, has been accurately encoded in a set of field equations. So let's fix a Boolean formula. We'll call it f. Its inputs are zi. Its output is z. Let's say, as an example, the formula might be z equals the conjunction of 3 inputs. We'll fix a system of field equations, phi prime. We'll assume that the system of field equations has distinguished variables corresponding to each Boolean input and output. So there will be a zi prime representing each zi, 1 if zi is true and 0 otherwise. We'll also assume that there's a z prime representing the output of the Boolean function, and there might, of course, be other variables as well that do not correspond to particular inputs or outputs. Our question is whether or not phi prime, which in this case might be z prime equals z0 prime times z1 prime times z2 prime, whether or not this actually represents the Boolean formula. And the definition, one of the definitions that we explore of correctly represents in this work is what we call the soundness condition, which essentially says if you solve the system of field equations, then you have an accurate evaluation of the formula. More precisely, here's the formula that expresses soundness. It says that if the equations hold and if every input is correctly encoded, so every field input is 0 or 1 according to its corresponding Boolean input, then the field output should be a correct encoding of the Boolean output. So that's one of the conditions that we'd like to check. How do we actually construct concrete verification conditions, not just in general? Well, we start by sampling a random Boolean formula. We run this through a ZKP compiler like Circe. That gives us a system of field equations. We consider mangling that system of field equations, I'll come back to that in a second, before we ultimately write down the soundness formula. We express that as a query to SMT, which reasons about Booleans and finite field operations. Finite field operations for the field system and Booleans for the formula, as well as the connectives associated in the soundness condition. I said that we might mangle the system of field equations. The reason for that is that we expect our compilers and other compilers will actually be correct on simple Boolean computations. And it's important that as we build a good tool, a good solver, we can reason not just about things that are correct, but also about things that are incorrect. Examples where the system is satisfiable, there's some counterexample. And so dropping one of the equations or performing some other destructive operation is a way of getting there. We're basically introducing bugs. Final note about our queries. Here, the prime is very big. In fact, for security reasons, most zero-knowledge proof systems require that the prime have 256 bits or similar. So that means the size of the field is 2 to the 256, which is absolutely huge. And this will end up being a problem or an opportunity down the line. Okay, so we've got these formulas, and we would like to improve an SMT solver so that it can reason about them. SMT solvers are complicated. I'm not going to explain them all right now. What I am going to say is essentially the core of what you need to do in order to add field reasoning to an SMT solver is you need to be able to solve systems of equations like this. A whole bunch of different polynomials ti in the input variables. So ti is a term in terms of multiplications and additions need to be 0. Is that satisfiable or not satisfiable? Is there a solution or not? And the way that we do this is basically by using ideas from computer algebra. The first tool that we use is called a Grosvenor basis engine, which is, in some sense, maybe the crown jewel of the field of computer algebra. It answers questions of the following form: whether or not t is in the ideal generated by the t sub I. You don't need to know what an ideal is. I mean, we need to know two things about this step for this talk. The first thing is that this step is potentially very expensive. Grosvenor bases take a long time to compute. In the worst case, that time is doubly exponential in the number of variables. In fact, if you've heard of Grosvenor bases, you've probably heard of that. The second thing that you need to know is that if 1 is in this ideal, that means our system is unsatisfiable. I won't talk about why, but it's not too hard to see. On the other hand, and this is unfortunate, the Grosvenor basis engine is not a good test for satisfiability. It would not be sound to conclude that if 1 is not in this ideal, the system is satisfiable. The problem here is essentially that the Grosvenor basis engine is too smart. What it's actually telling us is whether or not the system of equations is satisfiable over any extension of the field that we've posed the problem in. If you're familiar with complex numbers or imaginary numbers, it's essentially telling us if there are any imaginary solutions to our system of equations. And I guess the bad luck is ours. We don't care about imaginary solutions. We want actual solutions. So what do we do? Well, there's another tool from computer algebra that you're supposed to use in this situation. This tool is called a field polynomial. It's a polynomial of the form x to the p minus x. And the idea is that if you add the field polynomials to your system, if you say x to the p minus x needs to be equal to 0, the only roots of that polynomial are exactly the elements of the field, 0 through p minus 1. There are no imaginary roots to this polynomial. And so if you add these polynomials to the system, then you're essentially forcing the Grosvenor basis engine to only find solutions in the original field, which is exactly what you wanted in the first place. So this is what you're supposed to do, but it does not work in our setting. And you might even be able to see why. Think about the degree of the field polynomial. That degree is p. P is very, very big. Look at the runtime of the Grosvenor basis engine. It does not like big degrees. And this is not just a worst case runtime in this case. If you code this up and do the experiments, this thing goes off the rails. You're never going to reason about even fields of size like 2 to the 12. Forget about something bigger than that. So we can't do this. Instead, we whip together a backtracking search. I'm not going to talk about how it works in this talk, but you can look at our paper if you are interested. What you should know about the backtracking search is that it's correct, so we can trust the output of it, either satisfiable or unsatisfiable. And moreover, in the worst case, it too can be slow. In fact, its worst case runtime is linear in the size of the field, which is obviously unacceptable in our use case. Hopefully that worst case runtime will not be realized. So this is ultimately the sketch of our decision procedure. And now I'll skip forward to the main experiment that we did to validate whether or not this approach was any good. In this experiment, we used a field of full size, 255 bits. It turns out that's what a particular zero-knowledge proof system uses. And we benchmark a number of different systems. We benchmark RSolver. We benchmark a dumber version of RSolver that I didn't talk about today. We also benchmark the approach where you take your field equations, turn them into bit vector equations, run the best bit vector solver in the world, which is bitfutzla on them. We also consider turning them into nonlinear integer equations using modulus operations. Here we would run one of the NAA solvers like Z3 or CBC5. And then finally, we consider sort of an interesting alternative, which is saying that it's not the field that's the problem, it's the Booleans that are a problem. Turn the Booleans into field operations, throw this into a computer algebra system. So this is our plot that shows the results. The x-axis is the number of benchmarks, number of verification problems that you can solve in an amount of time given by the y-axis. If we had more time and this was a better setting for interaction, we could guess how the solvers do. We won't do that right now. I'll just put them up. The first thing to see is that the existing approaches, they just don't do well, and we shouldn't have expected them to do well. Bit vectors are not reasonable at bit widths of this size. Nonlinear integer reasoning is very hard in general, and the modulus is not helping. And then a computer algebra system is not a good stat solver. Computer algebra systems, unfortunately, have never been good stat solvers. Maybe one day that will change. On the other hand, the field approach does very well. And this worse version that I did not talk about indeed does worse. OK, so this is the main experiment that we do. Of course, there's a lot more on all fronts, really, in the paper. We don't just consider soundness. We consider another property called determinism, which is weaker than soundness, but is interesting because you do not need to know the specification, the intended functionality f, in order to write down the determinism condition. We also give the full decision procedure, how the backtracking search works, why this works for all finite fields, not just prime ones. And we talk about how we compute something called an unsatisfiable core, which is based on a really cute calculus for proving properties about ideal membership. And then we do lots of benchmarks to try to understand the performance of the solver, how we trade off against bit vectors, how we trade off against an approach where you use field polynomials, and basically why all these other things go off the rails and when. As for future work, I'm a bit short on time, but I'll say one thing that we're interested in doing is getting the worst case runtime of the backtracking search down from log in the field size to, from linear in the field size to log in the field size. We actually have the beginnings of an idea that we think might do this, so we're very interested in this. And if you're interested in learning more about computer algebra, either in theory and practice, please reach out to us because we would love to have collaborators on this journey. And I'll skip the rest for now. So I'm short on time, but I did promise I'd talk about Cersei, so I will.
I will not cut you off.
OK, cool. So after we had built this solver, one of the things that we wanted to do is take it out for a spin and actually do some automated verification. And the tool that we chose to attempt to verify was part of SERSI, this compiler infrastructure that Fraser was talking about. So zooming back out, this is the picture I showed at the beginning. We're trying to verify the first stage of this pipeline. Indeed, our benchmarks, while we were building the solver, were oriented around verifying compilation, but in a very restricted sense. They were doing translation validation, looking at particular input-output pairs for the compiler and checking that the compiler had executed correctly in that instance. Of course, what you really want to do is verify that the compiler is correct for all inputs, and that's what we do right now. So here's a quick overview of SERSI as it applies to zero-knowledge proofs. You start with the high-level program, you run the front end, you get to IR, you optimize and simplify the IR until you get to a very simplified IR that just contains Boolean operations, bit vector operations, fixed width integer operations, and field operations. And then you turn that into field equations in a process that we call finite field blasting. And this last step is the step that we chose to focus on because it's the most field intensive of all the steps. And also because we thought that there might be bugs in it. And so what do you see when you look inside the finite field blaster? Well, basically it's just a big bag of rules. There's a different rule for how to represent each operation in the IR in terms of field operations. In fact, some rules that even some operations have multiple rules. And there's like a whole system of encodings. There's like different rules for introducing private and public variables. All in all, there are about 80 rules here. And so we knew that the focus of our verification attempt had to include an automated way of processing these rules because they change all the time and because there's so many of them. And that's basically what we did. So the rules are applied in some kind of traversal over the IR that suggests that we're looking for an inductive proof. The notion of producing valid encodings of intermediate results in the IR that corresponds to some kind of inductive invariant. And basically what we want to check at the end of the day is just that each rule is preserving that inductive invariant. And we can write down SMT queries that check that fact, and then we can throw them into CVC5 and verify that they hold. Unfortunately, we did actually not verify that they held. We found a few bugs in the process, including one serious bug that would allow a prover to lie about essentially the results of any bit vector comparison. And yeah, these bugs, they just jump out at you when you're taking this approach because the SMT solver says, no, that property does not hold. Here is a counterexample. Okay, so all in all, I've been telling you about our work reasoning about satisfiability modulo finite fields. To our knowledge, this is the first real SMT solver that can solve equations over a finite field. We gave the first set of SMT benchmarks that involve finite fields. They corresponded to translation validation queries for zero-knowledge proof compilers. And then we took the solver out for a spin and used it to partially verify the final component of SERSI's ZKP compiler, which is the finite field blaster. And then what I'll say is one thing that we're very excited about is that we think that this SMT solver opens doors when it comes to doing cryptography-aware verification because finite fields are not just important for zero-knowledge proofs, they're important for a lot of cryptography. And we've done our best to make the finite field solver very accessible. So it's available right now on the CVC5 main branch via all the APIs of the solver, Java, C++, Python, or the textual SMTlib API. Please take it out, try it. And we've been working with people who have been using it already, both in industry and in research, and seem to be getting a lot of mileage out of it, which is great. And then I told you, of course, about our particular project using this solver to reason about SERSI. So thank you very much for your attention. It's been an honor to tell you about all this. And if you have any questions, I'll try to answer them.